Hello everyone, I'm Robin, and back in December I wrote a way too long blog post on Time-To-First-Byte, which you can read on the performance calendar below. For today, I don't have time to go through all, so instead I thought I'd just give you a very simple thesis instead that I'm going to explain, which is that Time-To-First-Byte is basically Frankenstein's monster of web performance metrics. Allow me to elaborate. As you probably know, Frankenstein's monster is not a real man, okay? He was built by using parts of corpses by Dr. Frankenstein. And so he is really an abomination, an insult against nature. And in the story, he ends up actually murdering several family members of the creator, and in some adaptations, even the creator himself. You can now see how this is exactly the same as Time-To-First-Byte. Of course, it is also not a real metric by itself. It's more like a compound metric. It's built up out of all these subparts, submetrics that come together to create an equally abominable thing. And while Time-To-First-Byte hasn't murdered anyone yet, it has definitely caused a lot of grief to its users, including you and me here today. And I think this has several reasons. One of the main ones is that we can't seem to agree on the definition of what Time-To-First-Byte means. Many people use different definitions. In my research, I found that most people use one of these three that are now on the screen, depending on the use case or the thing they're trying to do. For example, the shortest one there, the request Time-To-First-Byte, I like to call it, that measures when the actual HTTP request is sent until the HTTP response is received. And that basically measures network round trip plus however long it takes the backend to reply to the request. So if you're optimizing your backend server, this is usually the TTFB that you want to be looking at. However, if you're optimizing the broader network or you work for a CDN like me at Akamai, you're also responsible for the entire connection setup. So you would also be interested in things like the DNS and the TCP setup as well. So I like to call that the connection TTFB. But by far, most people seem to use this other definition, which kind of measures from when a user clicks a link on a web page. That's when it starts, when the link is clicked, until when that first byte of the HTML response arrives. So this is the longest. That's why I'm calling it also the navigation Time-To-First-Byte. And you can see, because it's doing this, it kind of works as a proxy for the actual end user experience. It kind of shows you how long the end user was waiting between the click and when the browser could start doing something useful when replying to that request. Now, we all use these different definitions interchangeably. And we rarely make it very clear which of them we're using when we're talking to other people. I'm going to give you a very concrete example. We had a customer at Akamai come to us and say, hey, we're having Time-To-First-Byte issues. And they meant navigation Time-To-First-Byte, because that is what they were seeing in the browser. And that is also what things like CrUX, the Chrome User Experience Report, with the Core Web Vitals, is also what it uses, the navigation Time-To-First-Byte. They told this, they didn't tell this to their Akamai team. They just said Time-To-First-Byte. Now, the Akamai team they talked to, they assumed it wasn't navigation, it was actually connection Time-To-First-Byte. Because why wouldn't they? Akamai has nothing to do with service workers, or we don't add extra redirects in the browser. We should only care about the networking part of things, okay? So they actually spent like 2 weeks trying to optimize the DNS and TCP settings, and it didn't really help. So they decided to escalate this to one of our backend engineers instead. Now, the backend engineer assumes Akamai is working correctly, is working performantly. He assumed it must be due to the origin, due to the customer's backend server that might be slow in responding to the requests. So he was using something more akin to request Time-To-First-Byte to try and analyze what was going wrong. This took about 3 weeks in total, and they didn't find the problem at all. And this is when me and my team got involved. And what we found out eventually, what was the actual problem, was none of these things. It was actually, predictably, redirects. They were using a bunch of third parties. that were bouncing between each other to do user tracking, and that added a bunch to the time to first byte. So this was super inefficient, a lot of wasted work, okay? It was like chasing Frankenstein's monster for 3 weeks because thinking he had murdered all the people, and at the end realizing, well, he's actually innocent. The real killer, well, that was a sparkly vampire dude from Twilight. It doesn't make sense, okay? Now you could say, Robin, I have a simple solution to this. We can just all agree to just use the same definition. From now on, time to first byte means navigation time to first byte, and we can all just live happily ever after. Well, that also wouldn't really work, because frequently some of these subparts of the compound metric will be 0 or very small. For example, if you don't have service workers, that's of course not going to be there. Or if you've already visited the site a while back, the DNS resolution might still be in the local cache, and the DNS part is going to be very small or non-existent. It gets even worse. Sometimes huge parts of this whole metric just kind of disappear. This is easy to see with, again, HTML navigations. The very first time you go to a site, you might have to do everything, right? You might have to redirect. Then you need to set up a new connection before you can actually get the HTML content. But after that, the second link you click, the third link, this connection is already established, and you really just need to send the HTTP request and get something back. You can see at the bottom that the part that is still left over there starts to look a lot like the request TTFB. Even though we're conceptually still measuring navigation TTFB, it kind of collapses down into this other type as well. You can see on the right there, it's of course also going to have very, very different measurements for that, very different numbers. The problem is we see all of this as navigation TTFB and put it all into one big bucket. All of that are our TTFB measurements. And if you then start plotting this as an actual distribution, so for example here in histogram shape, you usually get something that looks a bit bimodal. So it has two humps. It's kind of like a camel, right? On the right side you have the hump for the slower page loads, so that's the initial cold page loads. And then on the left you have the faster ones, which are hopefully more. You will have more fast page loads than slow ones on your site, I hope. So I think we can agree this is a relatively complex distribution of data points. And yet, we often make a mistake, is that we try to collapse all of this down into just a single number. Nowadays, the P75 to 75th percentile is very popular for that. A lot of people are using that. And conceptually, that's what you should do, right? Because a percentile is an idea, is a good concept to get one number to be representative for an entire distribution. However, I would argue that for this type of complex distribution, it doesn't work all that well. This P75 isn't really representative for what this thing actually looks like. And it gets way worse when you try to compare different distributions to each other. For example, this one comes from real user monitoring, real user measurements. So you will have people who visit multiple pages in one session. However, if you use synthetic testing tools, they much more commonly just load one page per session and always initiate the full connection, always get the slowest experience. So the distribution for the synthetic measurements might look very, very different, as we can see on the right. And yet, what is often done is that they just take the P75 for both of these and try to directly compare them. And you obviously get very confusing results that are difficult to interpret because of that. It's so weird that people do this. I like to compare this with, let's say, comparing Frankenstein to Donald Trump, right? These are clearly not the same thing. They do not belong together. One of them is an abominable monster, while the other is a misunderstood creature with daddy issues. They are not the same. And yet, I compare them here. And this is what we often do with time-to-first-byte metrics as well. Even though we get very different results, we put them in one bucket, and we compare things from two completely different tools, even though they shouldn't be. Now you can tell me, Robin, oh, rum versus synthetic. Everybody knows you shouldn't compare that. That's, of course, going to give you very different results. But sometimes this even happens within the same tool, within the same measurement approach. This is, for example, true in the current Chrome user experience report in CrUX. CrUX contains a number of different metrics, time to first byte, but also first contentful paint and largest contentful paint. The thing is, the distributions for these metrics are not the same. For time to first byte, as you can see here in the doc, time to first byte is only collected for full page loads, which means it's not collected for things like back-forward navigations or pre-rendered pages. But those are included in the LCP and FCP datasets. What this means is that sometimes you get very counterintuitive results. Here, for example, we optimize time to first byte by 50%. It halves, and yet it has no impact on the corresponding first contentful paint metric, even though we definitely expected it to. That doesn't mean things went wrong. It's just because these are two different distributions, and the right one simply didn't change the P75 enough to be registered. This is an example where time to first byte lowers, the rest doesn't. We also saw the opposite, where we added an optimization, and LCP improved in CrUX, but TTFB did not. It actually got worse, which is very surprising to us, which is not something we want to see, or at least our customer didn't want to see that. The reason, so what was the optimization that we added? It was the new speculation rules API. Okay, so as I said before, normal navigation time to first byte is registered or starts when the user clicks on a link until we get that response back. With the speculation rules API, the browser can start loading a page, for example, when a user hovers over a link, and the browser already starts loading the page in the background. Now the thing is, time to first byte is measured still when the user actually clicks. It doesn't start on the hover, it starts on the click. So by that time, hopefully, that's the whole goal of pre-rendering here, your time to first byte will be 0 or very short, and the same for LCP. So we would expect with this, both LCP and time to first byte would be very small. And yet, that's not what we see. Only LCP does that, and first byte actually went up. And the reason for that is exactly the same as the previous one. So let me put that up again. The time to first byte in CrUX, those measurements do not include the pre-rendered pages. So what happens if you enable pre-rendering? You go from an existing distribution with all or most of your page loads, but then a bunch of those page loads become very fast because they're pre-rendered, but they are removed from that distribution. They are no longer in CrUX because they're not collected, which means you're left with fewer data points that all represent the slowest part of your website. And that can then cause your P75 to shift to the right, to degrade your time to first byte, even though on a whole, your site actually became faster, even for TTFB. Now, let me make one thing very clear. I am not dunking on CrUX, okay? I love CrUX. I think CrUX is an amazing, excellent project. They're not doing anything wrong here. A lot of this is simply inherent in the way that statistics work. And there's sometimes no clear good choice to make for a lot of these things. It's not clear if one decision is better than the other, okay? And you end up with these kind of discrepancies that are simply inherent in this kind of complex system. The problem is just that too few people are aware of all of these nitty-gritty details to properly deal with the outcomes. All of that combined means that, at least in my opinion, currently it's nearly impossible to meaningfully compare all these different time to first byte measurements, especially between different tools and different measurement approaches, but sometimes, as we see with CrUX, even within the same tool. It's almost impossible to do this correctly. And what's the problem? Of course, This is exactly what people are doing in the wild. People are using time-to-first-byte to competitively compare two different, let's say, deployments or setups or CDNs to see which one is faster. And it doesn't always make sense. To illustrate that, let me end with one of my favorite examples of this, which has to do with a relatively new feature called 103 early hints. Early hints can be used to kind of make use of network idle time. So on the top, there's no early hints, and we are stuck waiting for a long time for our backend again to reply. The backend here is slow. If we enable early hints on the bottom, what you can see, while we're waiting for the backend to respond to HTML, we can actually have the browser load all kinds of stuff in the background already, so that all of that is done and ready by the time that the HTML comes in. And the way that practically works is that, for example, in this case, a CDN can send what is called an informational HTTP response. So it's like a temporary response. It has the response code 103, which is why it's called 103 early hints. And it's really just a link of preload and pre-connect statements that you might also put in your HTML, but then in HTTP headers. And then after that, it's followed by the final response, in this case, a 200 OK that you might be used to. Now, why does this matter in the context of my talk today? Well, you can now ask yourself, which of these is the first byte, right? Because if there wouldn't be 103 early hints, the first byte would be the 200 OK, containing some of the initial HTML data. And so you could say it should still be the 200 OK, even with the early hints. You could also make the opposite case, being like, well, literally the 103 early hints are the literal first byte that you receive. And these preloads and pre-connects are probably useful stuff that improve the user experience. So those should be counted in the time-to-first-byte as well. Predictably, when they rolled this out initially, people did not agree on which of the two approaches would be best, obviously. Firefox and Safari picked the literal first byte, so they had the 103 early hints if they were available, while Chrome did some additional work to rather keep the 200 OK, or the final response, as the actual time-to-first-byte. So what this meant was time-to-first-byte improved on the left browsers, but it stayed the same in Chrome, which again was very confusing for a while. Since then, Chrome has updated, and it now does the same as the other browsers. So all the browsers now use early hints. If they're available, early hints are counted as the endpoint to time-to-first-byte. But this means that using these early hints, you can easily manipulate your time-to-first-byte. You can easily make that metric better just by sending these early hints. And that's what causes a small exchange on Twitter about 2 years ago now. Initially, the CEO of a company called Shopify posted this, where it's like a benchmark comparing different types of hosting platforms, where Shopify was shown to be the fastest. Otherwise, he wouldn't have shared that probably, right? So Shopify had an excellent time-to-first-byte. We are the best in the world. This was then replied to by the CEO of another company, a competitor called Vercel, who were not doing as well on the same benchmark. And so he was saying, oh, that's not really fair. The only reason that Shopify is winning is because they're using these early hints. And that gives them an unfair advantage on the time-to-first-byte. And they're not even doing anything useful with the early hints. They're just sending one pre-connect, which doesn't do all that much in practice. That was his argument. And I hate to admit it, but he kind of has a point. It's not extremely fair to compare a site that uses the early hints versus one that does not, because the second one that does not, if they started using early hints, they would probably see an equal time-to-first-byte advantage as the first one. Okay? And it seems, apparently, Vercel agreed with me on that. So what they did in response to this was start sending their own early hints on the wire as well, but they did so in the worst possible way imaginable. they are sending useless links in there. They don't have a pre-connect, they don't have a preload, they just have some random headers that don't actually improve user experience at all. They're really just hacking the time to first byte metric. This is very different from Shopify, who were actually constantly iterating on their approach with this. Their initial version might indeed not have done all that much, but by now they actually have a quite sophisticated system in place for this that tries to intelligently add, things like preloads to actually improve user experience. And they have a very interesting blog post on this that you should probably read and check out. But so what we can see here, and I love this story because of this, is that at the beginning it seemed like Vercel was the hero of the story, right? They had identified this abomination, this monster on the internet, and they were going to stop its murderous rage. But in the end, it turned out that Vercel themselves were the real monster all along. Okay, an important lesson for everyone to follow there. Now, I like this setup. What happened, because it teaches us a lot of important lessons. Okay, it teaches us to be careful when we change how metrics are calculated, when comparing different deployments, but especially also that you shouldn't cheat metrics just to pretend to be faster, right? Like the age-old Charles Goodhart said, if a measure becomes a target, it ceases to become a good measure. It becomes a useless measure there, which time to first byte in these situations arguably has. All right, now I could keep going. The blog post has many, many, many more things, including this amazing picture which features an actual dinosaur. Okay, so that should be enough incentive for you to go and check that out. But we don't have time today, so let me wrap up with something that is hopefully coherent. You may have noticed I am not the biggest fan of time to first byte as a metric. You may have noticed that. However, I am also not naive. Okay, I understand that it's a very popular metric. It's going to be around for a long time, and people like to use it. I also understand that sometimes it can be a useful thing. I do like this quote by Barry Pollard as well. He says, time to first byte is good for telling you that something is wrong. It just doesn't tell you what is wrong, but at least you have some kind of high-level signal to know that that is going on. Okay. So I do agree with that. And so I wanted to end a little bit on a positive note. In my opinion, if you do want to use time to first byte, what should you do? You should primarily use it to measure changes over time for a single website or single page using one tool. In that context, you could probably get fair and consistent results that are effectively comparable, and that might give you the one metric or the one outcome, the P75s that you can share with your marketing teams and your business leaders and that kind of stuff to show you how you're doing on performance. What you should not be doing is using this to do all kinds of comparisons, comparing deployments, comparing different companies, and comparing different tools, because you are very likely to make mistakes, not account for all the different variables, and you're going to get very confused when trying to compare those singular numbers that come out of that. And I think that is a general good lesson in life as well, which we were also taught by Frankenstein, right? Because Frankenstein made that mistake as well. The monster, he tried to compare himself to us humans. He thought he had to be human. He thought he even needed a partner, a mate, a bride, which all ended in tears. So I think that is a good way to end with some good advice. Stop trying to compare yourself to others and just do yourself, do what you like to do, and everything will be better. With that, thank you all for your attention, and if there are any questions, I will be happy to answer them. Thank you.